Okay, in this video I'm back. I'm doing more Taylor series free response with error-bound questions. So, function f has derivatives of all orders for all real numbers x, and we're looking at a picture of, I know this one, of the graph of f and the tangent line and higher order derivatives. So I think we've actually already worked with this situation once earlier, maybe in the notes or something. But what we are supposed to see from this is right here. Okay, so the point they share is f of 0 equals 3. So when n equals 0, the zeroth derivative, I've got f equaling 3. And then the slope of this line here is going to be negative 2. So the first derivative is negative 2, and we can fill out the table that way, and that might be helpful for us as we work this question. So write the third degree Taylor polynomial for f around x equals 0. Yeah, exactly. So we're looking for f of 0 plus f prime of 0 divided by 1 factorial times x to the first, f double prime of 0 divided by 2 factorial x to the 2, and f triple prime, yeah, because we're looking for third degree, divided by 3 factorial x to the third. Okay, and then you could erase and fill in with those numbers, or you could just rewrite it and say, all right, that's going to be 3 minus 2x minus 23 over 2, that's the derivative, divided by 2 factorial. Don't make it too fancy because we don't have to simplify. If we need to simplify later in the question, we can just do it then. Plus f triple prime would be, oh wait, I messed something up. Okay, f triple prime is the one that's negative 23 over 2. F double prime was 3. So then negative 23 over 2 divided by 3 factorial x cubed. All right, there we go. We've written the third degree Taylor polynomial for f around x equals 0. First three non-zero terms of the Maclaurin series for e to the x. Okay, well, 1 plus x squared over 2 factorial plus dot dot dot. Second degree Taylor polynomial for e to the x, f of x. Okay, well, I'll just, second degree polynomial for f, 3 minus 2x plus 3 halves x squared, minus a term, but, we're not going to need to worry about that. We're going to set up for long multiplication with e to the x against f of x, which would be 3 negative 2x and 3 halves x squared. Right, and then we're just going to multiply. Multiply all these by 1. These will all be things I'm interested in. Okay, 3x, negative 2x squared, and I'm not going to be caring about this term because that would be degree 3. Okay, 1 half x squared, that would be 3 halves x squared minus 1x cubed. Okay, that's too much power, and so is that. Okay, so that's all the terms I need. So e to the x, f of x, okay, for constant, I'll have 3. X is negative 2 plus 3 would be positive 1x. X squareds, I'd have 3 halves plus 3 halves would make 3 total x squareds, minus 2 would be 1, so 3 plus x squared. And that would be the first three terms of e to the x, f of x, and I mean, if I was going to present this as my answer in the free response section, I might just say first three terms of this, and throw a nice little box around it and just walk away. All right. And so h is the function defined by the integral from 0 to x of f. Taylor polynomial in A to find an approximation for h of 1. Okay, so we're going to need... Okay, so I guess we're just going to use the... We're just going to write a Taylor polynomial for h using an antiderivative for f. This is just like not that specific. It doesn't say what degree to use. And it's like, you could use one higher, but I think they're probably going to ask about the error after. Yeah, exactly. Okay. All right. So we're going to go over here, and I bet there's going to be some pattern. Something here, and it went up to degree 4. That's an alternating series. Look at this close. All right, now this one just is a little strange. I just haven't worked this one in a long time. We wrote an equation for f of x, and this the Taylor polynomial, so we're just going to integrate that. So we're going to approximate h of 1 by integrating from 0 to 1 on f of t dt. And so really it would be equal to that, but I'm going to approximate it by integrating 3 minus 2x plus 3 halves x squared. Okay, 3 factorial is 6, and I'm going to multiply that by 2 and get 12, so minus 23 over 12x cubed. Okay, don't love that, but that's all right. I'm going to anti-differentiate 3x minus x squared plus 1 half x cubed minus, okay, add 1 to the power, divide by, okay, 23 over 48. That's a strange one. Okay, now I'm going to think about taking the derivative of this thing, because I went pretty fast on that antiderivative. 3 minus 2x plus 3 halves x squared minus 23 times 4 over 48. That would be 1 over 12. X to the 3. Yeah, okay, I feel good about that. Then I'm going to let x run from 0 to 1. Okay, and, the whole t thing, don't even worry about it, right? If we just anti-differentiate the polynomial we had, plug in top and bottom, subtract, which I think is what y'all would want to do. I'm actually going to give myself a little more room. So that would be equal to 3 minus 1, when I plug in x equals 1, plus 1 half minus 23 over 48. And then when I plug in 0, I'm going to get a bunch of zeros. Okay, they would all add together to be 0, and that's going to be my answer, right? I don't need to simplify that. Okay, it is known that the Maclaurin series for h, which we just kind of approximated, converges to h of x for all real numbers x. Okay, that's nice. It's also known that the individual terms of the series for h of 1 alternate in sign and decrease in absolute value to 0. Use the alternating series error bound to show that the approximation found in part C differs from h of 1 by at most 0.45. Alright, so this is an error situation. They used the words alternating series error bound, so that's polite of them. They also gave us that clue that individual terms of the series alternate in size and decrease in absolute value to 0, and that's also a giveaway that you're going to be using the alternating series test and probably the alternating series error bound. So error is no more than the absolute value for the alternating series. This is the next term. Okay, now the next term was going to be, let's think about that. I guess okay, so at this point, I think I need to backtrack a little bit and go back to, the Maclaurin series for f. Okay, so the first neglected term for that one would have been n equals 4, so that would have been a 54 over 4 factorial x to the 4. So what was the last one I did right? It was negative 23 over 12 x to the 3. And then the next one was going to be plus 54 over 4 factorial. Let me make sure that's what that was, right? Yeah, 54 over 4 factorial x to the 4. So g, or is that what it is? No, h, which is an antiderivative for f, is going to have some stuff. And we get up to that fourth power term, which is what we use, negative 23 over 48 x to the 4. And we need to antidifferentiate this thing. So that would be 54 over 5 times 4 factorial. This is going to be 5 factorial. That's where that factorial is coming from. I was thinking about doing this a different way, and I just wasn't seeing it. Okay, so then when I plug in x equals 1, I'm going to, right, yeah, it differs from h of 1. Yeah, so we're approximating h of 1, so we plugged in x equals 1. That would be 54 over 5 factorial, which must be 0.45, so 5 times 4 times 3 times 2 times 1. Maybe I think about 54 as 6 times 9, so 6 times 3 times 3. And then those are going to cancel, and then I would have 5 times 4 is 20, times 2 is 40. So 9 over 40 is that 0.45. When we don't know, we just say equals 0.45. I can kind of see why. Okay, so it would be 40 times 2 is 8. So times 2.5. Hold on a second. I feel like I've done something wrong here. Yes, that's because I had 6 times 3 equals 9. As soon as I paused it, I saw that. So 6 times 3 is 18 over 40. 2.5 18s is going to be 45. Yeah, that makes more sense. Okay, because 2.5 40s is 100. 2.5 18s is 45. That would be 45 over 100. There we go. That's more like it. Okay. Those are sometimes tricky, I'm trying to figure out the arithmetic. But the next one is a function of f having derivatives of all orders for all real numbers x. Assume f of 2 equals -3, f prime of 2 is 5, and so this is basically just a table, right? The third degree Taylor polynomial for f around x equals 2 and approximate f of 1.5. Okay, so third degree Taylor polynomial. Just gonna call it T3. This is going to be equal to f of 2 plus f prime of 2 times x minus 2 plus f double prime of 2 times x minus 2 squared divided by 2 factorial. I almost forgot. I was not just saving it for the end. Plus f triple prime divided by 3 factorial x minus 2 to the third. Okay, then we're going to use that to approximate f of 1.5. So f of 1.5 is going to be approximately equal to T3 of 1.5, which is equal to -3 plus 5 times 1.5 minus 2 is -0.5 plus 3 over 2 times -0.5 squared minus 8 over 6 is going to be 4 over 3 times -0.5 to the 3. And we're not going to be wanting to compute that. Okay, that's just going to be where we'll stop. Fourth derivative of f satisfies the inequality there for all x in the closed interval 1.5 to 2. We're going to use the Lagrange error bound. Okay, so that's always going to start off with error less than or equal to. For f of 1.5 found in part A to explain why it's not equal to 5. Okay, so this is kind of like the other one where we showed it wasn't a negative number. I think that's more of an older thing. Now they're just trying to, now you're just finding the error bound, it seems like. I haven't seen one of them like this in quite a while. That doesn't mean that we're not going to see it this year, but, I haven't seen it recently. So, error less than or equal to, okay, we used a third degree polynomial. So, we used n equals 3. Our polynomial was centered at 2, and we approximated at x equals 1.5. Okay, so that'll have to do the next factorial, and then the next power of the absolute value of 1.5 minus 2, or you could do 2 minus 1.5, it really doesn't matter, to the n plus 1 would be fourth power, and then we're going to have this value right there, this m. Okay, so m is the maximum of the absolute value of f's fourth derivative on the interval 1.5 to 2, interval between the centering point and the approximation point, but that's sometimes subject to change, whether it's on the left or the right, which spot each one goes in. So that's why I'm saying, at this point, being the type of person that is great as this type of problem before, I'm really not recommending that you write any of this stuff because they already gave it to you, and especially with this one where they give it to you in the statement of the question, we're just going to go ahead and say, all right, well, that number that we're looking for is right there, it's 3. And so we're just going to use it, okay? And then if we use it and we write it out like this, we're going to get the point for the form of the Lagrange error bound because it's implied by the way we wrote it. 3 over 4 factorial times the absolute value of the difference between the approximation point and the centering point to the next power. That shows that you know what you're doing with the Lagrange error bound. So I've kind of changed my tune. That's why I'm re-recording the homework solutions. I think we need to just go straight for it. Now, we need to show why this is not equal to -5. And that's a little bit more challenging, like I said, and that's why it's good for homework, maybe more so than a quiz or a test. So 3 over 4 times 3 times 2, 1.5 minus 2 is a half to the fourth power. So that would be 1 over 4 powers of 2. Okay, so 3 over 3 here. Okay, so this is less than or equal to 1 over 4, 5, 6, 7 powers of 2. Okay, 2, 4, 8, 16, 32, 64, 128. Okay, so this must be a calculator question. Yeah, I think I remember that 1999 they were allowed a calculator on the whole thing. So they must have needed to find the approximate value of f of 1.5 that they got using the Taylor polynomial. Let me calculate that real quick. Okay, great. I looked it up. It's negative 4.958. Okay, and the error is less than or equal to 1 over 28. Okay, so if the error is less than 1 over 28, I already forgot, negative 4.958. So the actual value of f of 1.5 will be between, okay, my approximation, negative 4.958, minus 1 over 128. And then on the other hand, I could have negative 4.958 plus 1 over 128. But I know that this is going to be greater than negative 5 because 1 over 128 is less than 1 over 100, and 1 over 100 would move it just 1 in the second decimal place. So that would be at most, negative 4.968. But we actually know it can't even go that far because it's 1 over 128, not 1 over 100. And so that would be how I would show that. But again, this is not really the problem type that we're seeing all that often anymore in AP calculus. So the next one is talking about write the fourth degree polynomial p of x for g of x equals f of x squared plus 2. Okay, fourth degree polynomial. Oh, we're gonna have we're gonna want to go forwards on this one, not try to plug x squared plus 2 into the polynomial for f. Although I think that would probably work. I don't know if that's, yeah, I would personally not. I don't know exactly what I'm looking at on the scoring guidelines, to be honest. I don't want to look that long, and I don't want to really pause and look either. So I'm just going to go forwards and just say, all right, no, but we need 4 orders of derivatives. I don't love that. Yeah, so I'm going to just write down the Taylor polynomial for f, which I'm kind of forgetting what that was. Oh, yeah, about x equals 0. Wait a minute. How am I supposed to know that? Let me look at this again. Okay, yeah, since I didn't know really any information about the derivative of f at x equals 0, I mean, maybe it would have worked out just right, but taking 4 orders of derivatives didn't seem quite right. And now I see what's going to happen with the algebra. So if this is a Taylor polynomial for f, right? Okay, so a third degree Taylor polynomial, or fourth degree Taylor polynomial for g is going to be, I'm just going to plug in x squared plus 2 wherever I saw x. So negative 3 plus 5 times x squared plus 2 minus 2. Right, so I'm just plugging in on this and this and that. And each time when I plug in that x squared plus 2, I'm going to subtract away that 2 and it's going to work out really nicely. Okay, now if I'm going for fourth degree polynomial, I'm only going to need this. Okay, so that would be an x squared plus 2 minus 2 squared. That's going to be a fourth degree polynomial. Again, I plugged in x squared plus 2 where I had seen x because of that composition of functions right there. And now I'm going to simplify some stuff, and that's going to be negative 3 plus 5x squared plus 3 halves times x squared squared would be x to the 4. This is really nice. Okay, so does g have a relative minimum at x equals 0? Yes, I see it. All right, so the lack of a x to the first term, 0x, I know that g prime of 0 equals 0, because this is a Maclaurin polynomial for g. And then when I see this positive 5x squared, I know that that means g double prime is a positive number. I'm still not totally sure if I can just proclaim that, so I'm just going to really quickly say that 5x squared equals g double prime of 0 divided by 2 factorial x squared, and that means that g double prime of 0 equals 5 times 2 factorial, which is definitely a greater than 0 number, so that means g has a relative maximum at x equals 0. And that was what they had asked us to show. Okay, now the last one here is this one. Okay, that's going to be alternating series error bound as well. And that's why I've got other extra practices on Lagrange error bound. At this point, I don't want to give you the wrong impression either, like you're going to be doing it a whole bunch of times. Like it's just something you're going to do once, right? Maybe if you've got 2 sections on an upcoming unit test, I'll have you do it once on each section, but it's not like that big of a deal. It's kind of like the derivative of the inverse function last semester. It's, something we have to know about, but it's not going to be like a huge portion of the exam. Okay, so that's why I've got these other types of questions in here too, because we're really starting to get to the point where we need to review all of our knowledge about series and Taylor series together. So find the first 4 terms in the general term of the Maclaurin series for f. Okay, we've done quite a few like that, at least this year. 1 over 1 minus x equals 1 plus x squared plus x cubed, and so on up to x to the n and beyond. And if we're just wanting to go right for it, okay, think about what we would plug in. That would be negative x cubed. I'm just going to plug that in on all of the parentheses. And there we have ourselves the first 4 non-zero terms and the general term of the Maclaurin series for f. And I really think that's the way to go. Set up the skeleton, plug in on it, especially when you see that coming. If you wanted to take the first 4 derivatives and plug in the values and make that happen, be my guest, but I just don't think that's the way to go. So find the first 4 terms in the general term of the Maclaurin series for f prime of x. Okay, now this is a situation where it will help us to kind of simplify the thing that we just created. So that's going to be 1 minus x cubed plus x to the 6 minus x to the 9. Okay, I'm going to write out the next term because I can see we're taking the derivative, and that derivative of 1 is going to be 0, so I'm going to need another term. It looks like it's going to be a plus an x to the 12, and then plus negative 1 to the n, x to the 3 to the n, which would be x to the 3n, and beyond. Okay, then that means that f prime of x is going to equal 0 minus 3x squared plus 6x to the 5 minus 9x to the 8 and 12x to the 11 minus ... And then what we did is it's still alternated. That didn't change by the process of taking the derivative. The power got brought down, and then we reduced it by 1. And then plus 8 ... Okay, and then we have ourselves a Maclaurin series for f prime of x. Okay, use the results from part B to find the sum of the infinite series negative 3 times, okay, divided by 2 to the 2, 2 to the 5 in the denominator. Okay, so what's happening is we've just got a 2 in the denominator, so I think this is x equals 1/2. Okay, so this series, to me, is looking like f prime of 1/2. Now, we know, oh yeah, we know f of x, so we should be able to find f prime pretty easily. F of x is 1 over 1 plus x cubed. So that's going to be equal to 1 plus x to the 3 to the negative first power. Okay, and then I'm going to take the derivative of this thing. That'll be negative of that thing to the negative 2 power times the derivative of that thing. And we leave the inside the same, right? So we use the chain rule, and we are going to say f prime of 1/2 is going to equal the negative of 1 plus something cubed to the negative 2 power times 3 times that thing squared. Okay, that's kind of a lot. But I think we could stop there, right? This is supposed to be just a number. As long as we're not going to use that, no, we're moving on to the integral of f. And so, first 4 non-zero terms in the general term of the Maclaurin series that represents the integral of f of x from 0 to x. Okay, so that's going to be the antiderivative of f that happens to have f of 0 equals 0, because you can envision plugging in 0 there. We've talked about this before. C is going to equal 0 if you want to think about it like that. However you want. But so what I'm going to do is, I think, did I have that? No, that was a totally different problem. Just grab this though, because we've already used that enough on that problem. So I'm just going to anti-differentiate term by term. So integral from 0 to x of f of t dt is going to equal, okay, I'll just go back through it. I definitely haven't done it in this video. C plus 1x minus 1/4 x to the 4, okay, plus 1/7 x to the 7, minus 1/10 x to the 10. That extra term really threw me off there, but that is 4 non-zero terms, so we're going to be happy. Yeah, we needed that other one because we were taking the derivative. So what happened was, it was still alternating. We added 1 to the power, and then we divided by the new power. Okay, now for the idea of c, we also know that the integral from 0 to 0 of f of t dt equals 0. So I should have 0 equaling c plus 0 minus 1/4 of 0 to the 4th, plus a whole bunch of other things that are all zeros. And so that means that c has to equal 0, and that's just how that's going to work. That's why, if the Taylor series is centered at x equals 2, and it'll always be the integral from 2 to x of f of t dt. And, we just kind of always know that c is going to equal 0. And that's just one of the nice things about AP Calculus. They really couldn't ask you about it centered at a different point. It would be, outside of the information that we have. But that's just a different discussion. Use the first 3 non-zero terms of the infinite series found in part D to approximate the integral from 0 to 1/2 of f of t dt. Okay, so, that's like taking this to 3 and plugging in 1/2. So I'm going to say, all right, the integral from 0 to 0.5 of f of t dt, that's going to be approximately equal to 0.5 minus 1/4 of 0.5 to the 4 plus 1/7 of 0.5 to the 7. Okay, what are the properties of the terms of the series representing this guy that guarantee that this approximation is within 1/10,000 of the exact value of the integral? So they're talking about an error type situation, and one of the properties of the series, we don't have to really worry about that with a Lagrange error bound. They usually just use the word Lagrange error bound, and we have some kind of information about the absolute value of the next derivative, and that's just really not what we've got here. So it must be alternating series error bound, and this was an alternating series. So what I might do is I might say the series that we wrote in part D, just the series for the integral from 0 to x of f of t dt is, well, it's alternating. Because of that negative 1 to the n power, decreasing in magnitude to 0. Okay, how I know they're decreasing is, what would I have? 1/2 magnitude. If I take the absolute value, get rid of the negative. 1 over 2 to the 3n plus 1 times 3n plus 1 is definitely decreasing. Okay, you don't need to show this, but I'm just going to show you my logic here. And, the limit of that stuff decreasing in magnitude to 0. Yeah, like even if I didn't consider the magnitude 1/2 to the 3n plus 1, even without a growing denominator, that would be going to 0. But even with a growing denominator, that's going to 0, so that's why that's working. But those are the properties. And then we would, 1 over 10,000, this one's pretty challenging, I think, if I recall. The next term would have been negative 1/10 x to the 10. Yeah, so error is less than or equal to the absolute value of the next term. So had I used the next term, it would have been negative 1/10 x to the 10, and I would have plugged in 1/2. So, wait, what was it? Negative 1/10 x to the 10. Okay, and then I plugged in 1/2, so about like that. And okay, and that's definitely less than 1 over 10,000. 2 to the 10 is 10, what is it, 1024? Yeah, 1024. So that's less than or equal to 1 over 10 times 1024, which is definitely less than 1 over 10,000. But if you didn't see that arithmetic happening, what you would do is you would just not include that bit and just say, well, I mean, as long as you write it correctly, 1 over 10,000, not 1,000, then you'll get your point. Okay, that's, we just had to justify the use of the alternating series error bound, what are the properties of the terms, and then, actually do the error bound and realize that, okay, the error was less than 1 over 10,000. Okay, that's all for this homework. Thanks for watching.